Welcome back to the Deep Dive. Today we're taking a really focused look at a foundational text in material science.
We are.
We're diving into the heart of thermodynamics, the part that really controls phase stability.
Right.
We're looking at heat capacity, enthalpy, entropy, and of course the third law.
And our mission today is to, move past the simple definitions you probably learned in your intro classes.
Right.
We want to get into the derivations, the applications, and I think most critically, how one simple measurement, how much heat it takes to raise a temperature.
Just one measurement.
Yeah, just that. How that simple thing becomes the absolute foundation for calculating everything you need to know about a system's equilibrium.
That sounds like a pretty powerful promise, that one simple measurement, CP, unlocks the whole thermodynamic universe.
It absolutely does. The entire chain of calculation, it all relies on having precise heat capacity data across a range of temperatures.
Okay, so let's start there. The basics, but with that thermodynamic twist. We've got heat capacity at constant volume, CV, and at constant pressure, CP. And for materials engineers, we mostly care about CP.
That's right, yeah, because most of our processes, metallurgical, ceramic, they happen at constant or at least ambient pressure.
So what is it exactly?
So CP measures the rate of change of molar enthalpy, which is H, with respect to temperature, T, at constant pressure. So mathematically, it's just the partial derivative, THEP.
And CV is the same thing, but for internal energy, U.
Exactly. But here is where it gets really interesting. And you start to see how deeply all these things are intertwined.
This is the Maxwell relations part.
Yes. You can connect CP and CV directly to the potential functions. The Gibbs free energy is G and the Helmholtz free energy A.
Okay, give me the equation.
The one we really care about is CPIETT.
Whoa! Okay, a second derivative. Let's unpack that because that is not intuitive at all. Why on earth does heat capacity relate to the second derivative of free energy?
Well, think about it this way. What's the first derivative of Gibbs energy with respect to temperature?
That's entropy S negative S, actually.
Right. So the second derivative is the rate of change of entropy with temperature. So if you have a high heat capacity, it means when you add heat, the temperature goes up slowly.
Which means the entropy of the system must be changing really rapidly.
Precisely. You are effectively measuring how quickly the stability potential of the system, which is G, curves away as you change the temperature. If that curve is very steep, your heat capacity is very high.
That makes so much more sense. It's a measure of the curve, not just the slope.
You got it.
Okay, so with that connection made, let's look at the temperature dependence of CP, starting with those old empirical rules.
Right, the simple approximations. So back in the 19th century, Dulong and Petit figured out that the molar heat capacity at constant volume, CV, for most solid elements approaches a limit.
The famous 3R value.
The 3R value, which is about 24.9 joules per mole Kelvin at high temperatures. And Kopp's rule just sort of extended that. It suggested for a compound, you just add up 3R for each atom. So a compound like ARB should approach 9R.
And this is great for, a quick back-of-the-envelope calculation. But it immediately falls apart when you look at real data, doesn't it?
It does.
Why do materials like copper and lead hit that 3R value near room temp, but something like silicon or, diamond is way, way lower?
It's all about the bonding and the temperature scale. That 3R limit is a high temperature classical approximation. Materials with really stiff bonds like diamond, you need much, much higher temperatures to get all the vibrational modes activated to hit that limit.
And at low temperatures.
And critically, at the lowest temperatures, CP for all elements just dives towards zero. That was the huge quantum mechanical insight from Einstein and Debye. Thermal energy is quantized.
So since CP is what we actually measure, we need a practical way to handle that temperature dependence. We can't just use 3R.
No, absolutely not. For any kind of engineering accuracy, what we do is fit the experimental data over specific temperature ranges to an empirical polynomial. Usually it's something like CP equals A plus BT plus CT.
And that equation is what lets you actually do the math to plug it into your integrals.
That's the key. For something like chromium, you need a complex fit that works all the way from room temperature up to over 2000 K just to capture its behavior.
Okay, but what about a wrinkle? What happens when we hit a phase transition, say zirconium changing from its alpha to beta structure at 1136 K?
Oh, okay. So if you're tracking the heat capacity as you heat it, you'll see CP rise pretty rapidly as you approach the transition. Then right at that equilibrium temperature, T trans, the heat capacity shows, well, it shows an apparent infinity.
An infinite heat capacity. That sounds impossible. What's actually going on there?
It's not really infinite, of course, but physically what it means is you're pumping in massive amounts of heat, and the temperature isn't budging. It's flat.
Because all that energy is going into the transformation itself.
Exactly. It's being consumed to break bonds and reform the crystal structure. It's not increasing the kinetic energy of the atoms, which is what temperature actually measures. And since Cp is defined by change in heat over change in temperature, and your delta T is basically zero, the value just spikes.
That makes sense.
Yeah.
Okay, so now that we have the CP data, we can move into calculating enthalpy.
Right. And the change in molar enthalpy, AH, between two temperatures, T and T, is simply the definite integral of Cp with respect to temperature. Visually, it's just the area under that Cp versus T curve.
And this is how we start defining whether a process is endothermic or exothermic.
Mm-hmm.
But what I find so fascinating here is how enthalpy's nature as a state function lets us completely sidestep some really difficult direct measurements.
Oh, it's incredibly powerful. Imagine you need to calculate the enthalpy of a phase transformation, like melting, but at some temperature, TO, where it doesn't normally happen.
We can't just measure it there.
You can't, but you don't have to. You can create a conceptual cycle that goes through the equilibrium melting temperature Ts.
Okay, so you would describe this cycle as, first you heat the liquid from TO to TU.
Right.
Then you let it undergo the standard phase change at T.
The normal melting enthalpy, yeah.
And then you cool the solid product back down from TO to T.
And since enthalpy is a state function, the sum of those three steps has to equal the enthalpy change of the direct path at T.
Amazing.
And when you analyze that cycle mathematically, you arrive at Kirchhoff's law. It states that the rate of change of the transformation enthalpy with temperature is just the difference in heat capacity between the products and the reactants. So, HTP into AP.
So if you know how the heat capacities of the two phases differ, you know exactly how the energy of that transition changes with temperature.
You do. And if enthalpy is close to zero, which it sometimes is,
Then the enthalpy of transformation is pretty much temperature independent. A huge shortcut.
a great insight. And to make all of this work on a global scale, we need a reference state, a 0 point.
Like at the convention.
The convention is we assign an enthalpy of 0 to all elements in their most stable start at 298 K, so 25 degrees C, and 1 atmosphere.
Which means if you look up the standard enthalpy of formation for, say, lead oxide, PbO, at 298 K, that value is the enthalpy of the compound itself.
Yes, because the reactants, the lead, and the oxygen are defined as 0.
It's a massive computational shortcut.
It is. And just to connect back to the physics, Le Chatelier's principle reinforces our sign convention. If you have a system at equilibrium, like solid and liquid ice and water, and you add heat,
The system has to shift to oppose the change.
right, so it undergoes the endothermic process, which is melting. This confirms that any change from a low temperature phase to a high temperature phase melting, boiling, it's always defined by a positive H.
Okay, so as CP and H established, we have to tackle the final piece of this puzzle, entropy, and specifically the third law of thermodynamics. Why was this so important to figure out?
Well, this was the holy grail for physical chemists in the early 20th century. They had the Gibbs-Helmholtz equation, GGHT,
The master equation.
the master equation. They knew H and S changed with temperature, but to integrate them and get the full picture of A versus T, they needed the integration constant. They needed to know the entropy change at absolute 0.
Without that constant, they were stuck. They couldn't calculate equilibrium constants from first principles?
They were completely stuck. And the first clues came from a chemist named Richards, who saw that for many reactions, the curves for A and H seemed to come together to approach each other asymptotically near 0K.
And since Deja approaching H means that T's term is going to 0, and the slopes were also going to 0, that implied that ACE itself must be approaching 0.
Exactly. Which led Nernst to formally propose his heat theorem in 1906. ACE is 0 for all reactions involving condensed phases at absolute 0. And then Planck and Simon took the final step, stating the third law as we know it now.
Which is?
The entropy, S, of any homogeneous substance in, and this is the key phrase, in complete internal equilibrium is 0 at 0K.
That qualification, complete internal equilibrium, sounds like it's doing a lot of work there.
It is paramount. Everything hinges on it.
So if we assume S is 0, what are the physical consequences? What does that mean for the ground state of a material?
It imposes incredibly strict conditions. For entropy to be 0, the system can only have one possible quantum mechanical microstate.
Perfect order.
Perfect order. This means stable phases at absolute 0 must have 0 configurational entropy. That completely rules out amorphous phases, glasses, and critically for us material scientists, it means stable alloys at 0K must be perfectly ordered.
So either pure elements or stoichiometric, fully ordered intermetallic compounds.
Right. Any frozen in randomness means S is not 0.
And the third law also constrains other properties, doesn't it?
Yes, using Maxwell relations, you can show that things like the thermal expansion coefficient and the thermal coefficient of pressure must also go to 0 as temperature approaches 0K. Everything just becomes flat and perfectly stable.
Which also gets us to the unattainability statement. You can't actually get there.
You can never cool a system to absolute 0 in a finite number of steps. It would violate the law itself.
Okay, let's go back to that crucial caveat.
Yeah.
Complete internal equilibrium. We know real materials violate this all the time. Where do we see this so-called residual entropy?
Oh, everywhere. Anywhere disorder gets frozen in, glasses are the classic example. They have the non-zero entropy of the liquid structure because the atoms just didn't have time to arrange into a perfect crystal on cooling.
In solid solutions, too.
Absolutely. Non-equilibrium solid solutions, where atoms are just randomly mixed on lattice sites, they retain that entropy of mixing.
The book has that great example with carbon monoxide, CO.
That's a fantastic one. You freeze CO into a solid, and the little CO molecules can orient themselves randomly, head to tail or tail to head.
And that randomness, even though it's all the same molecule, leads to a measurable residual entropy at 0K.
It does. It calculates out to 5.76 joules per mole Kelvin, a non-zero entropy at absolute 0, which just proves the system did not achieve that state of complete internal equilibrium. The law holds, but the material didn't meet the condition.
So now that we can define S as 0, calculating the absolute entropy at any normal engineering temperature becomes pretty simple.
It's just an integral. S at temperature T is the integral from 0 to T of CPT dt. You integrate the heat capacity divided by temperature, and of course you add in the entropy of any phase transitions, like melting or boiling, that you cross along the way.
And we also have some quick sanity checks, some rules of thumb for those transition entropies. Richard's rule, for instance.
Right. It suggests that molar entropies of fusion, LSM, are pretty constant for similar crystal structures, about 9.6 JK for FCC metals.
And Troughton's rule does the same for boiling.
Yep. The molar entropy of vaporization is about 87 JK for many metals. They're just invaluable for preliminary modeling when you don't have all the precise CP data yet.
Okay, last big topic. Let's quickly address the influence of pressure on enthalpy and entropy.
Right, we can derive the dependencies using Maxwell relations again.
Yeah.
We get HET V1 HET and HET of V.
But while the derivations are important, the practical takeaway for materials engineers is actually pretty simple, isn't it?
It's very simple. Condensed phases, solids, and liquids are, for the most part, incompressible.
And the iron example in the text really drives that home. Even if you crank the pressure up by 100 atmospheres, the increased molar enthalpy is only about 71 joules.
Which is equivalent to heating the iron by just 3 Kelvin. It's tiny.
And the entropy change is even smaller.
Almost negligible. So for most practical applications, involving condensed phases between 0 and maybe 10 atmospheres, we can confidently ignore the influence of pressure on H and S.
So to synthesize this whole chapter then, we started with simple heat capacity measurements.
Right, with CP.
We used that data, combined it with a standard reference state for enthalpy, and the third law's postulate of zero entropy.
To calculate the full temperature dependence of both HT and ST.
Which then lets us calculate the Gibbs free energy, GT.
Giving us the ultimate criterion for predicting the stable phase, the equilibrium state, for any system at any temperature we care about.
We've established that the third law is this beautiful, conceptually necessary framework, requiring systems to approach perfect order at 0K. But that critical condition is complete internal equilibrium. So given that every single industrial process casting, forging, welding, any kind of cooling, involves finite cooling rates, and almost always results in frozen-in disorder, solid solutions, and non-equilibrium phases, how confident should we really be in using that fundamental assumption of S00 when we're designing new alloys or predicting phase stability in the real messy world? Does the elegance of the third law sometimes lead engineers astray? What stands out to you?
That is the real challenge, isn't it? That's what every materials engineer faces.
Thank you for joining us for this deep dive. This has been a concise recap of the chapter's essential points and a warm thank you from the Deep Dive team.